All right, let's jump right into this explainer. If you've been writing Python for a while, you're probably ready to graduate from basic scripting to true enterprise-grade architecture. And we're going to do exactly that today by reverse engineering the actual source code behind the OpenAI Agents SDK. Seriously, be honest for a second. Have you ever opened up a massive professional GitHub repo, like, say, OpenAI's, and just felt completely lost? Like you were trying to read an alien language? Yeah, we've all been there. It's totally overwhelming. But stick with me, because by the end of this explainer, we're going to decode that completely. So here's the game plan for today. First, we'll look at the sheer power of Python data classes. Second, we'll break down Python callables. And finally, we'll master generics. Let's get right into it.
All right, part 1, the power of Python data classes.
Take a look at this. Data classes are actually a foundational tool that OpenAI uses for literally over 90% of the classes in their Agents SDK. And it's obvious why. On the left, you've got your standard old-school Python class. You know the drill: manual constructors, endless verbose self-assignments. It's clunky. But on the right, just by popping that @dataclass decorator on top, all that noise completely vanishes, leaving you with this beautifully clean, instantly readable structure. So what's actually happening behind the scenes here? Well, data classes are basically writing all that tedious boiler code for you. They automatically generate your init constructor. They whip up a Reaper method, which means your object actually prints out as a nice, formatted string instead of some random, messy memory address. And it even writes the EQ method, so you can easily compare two instances based on their actual data, not just where they live in memory. It saves a ton of time and honestly just wipes out silly human errors. But here's where standard classes lay a really dangerous trap, especially with default values. Think about it. What actually happens when multiple object instances share a default mutable list? If you assign an empty list as a default variable in a normal class, multiple objects end up accidentally sharing the exact same memory location. So you append an item for one user, and bam, it accidentally shows up for everybody else. It's a huge headache and a really common bug. Enter the lifesaver. Default factory equals list. Instead of tying a single empty list to the entire class, this neat little method dynamically generates a fresh, totally isolated list for every single new instance you create. It guarantees that every object gets its very own unshared memory space. Boom! Those terrifying shared memory bugs, completely gone. And here's an awesome bonus. Structuring your data this strictly actually has massive downstream benefits. It lets automated tools like MDocs sweep through and generate absolutely gorgeous structured documentation straight from your code variables and type hints. I mean, this isn't just a cool theory. This is exactly how OpenAI automatically generates their stunning API docs directly from their source code. Moving right along to section 2, understanding Python callables. Let's talk about how Python treats functions as actual objects using callables. To keep it simple, and I love this analogy from our source material, think of functions kind of like your servants. You hand them specific inputs, they go off and do the work, and then they hand you back an output. But how do we actually enforce that contract strictly in our code? That's where this specific type hint syntax comes into play. You literally just write callable followed by brackets. This clearly tells anyone and any static checker that this particular function needs exactly 2 integers as input, and it absolutely promises to return a string as output. Any dev looking at this instantly knows exactly what this servant needs to do its job and exactly what it's going to hand back. The real magic of callables is how incredibly dynamic they make your code base. You can just pass functions around as variables straight into your classes. You can even use the magic call method to turn an entire object instance into a function itself. OpenAI heavily relies on callables to dynamically pass complex instruction behaviors around inside their SDK, and they do it without ever sacrificing strict type checking. It's pretty brilliant. All right, on to our final and maybe most exciting section, mastering generics in Python. This brings us to handling completely unpredictable data dynamically. Let's say you write a function, but you honestly have no idea what data type the user is going to pass in. The easy way out is to just slap an any type on it and call it a day. But what's the actual danger of doing that? Well, to be blunt, using any opens up massive vulnerabilities. It completely nukes your type information. It essentially acts as an off switch for your static type checkers. You are literally disabling Python's safety nets and leaving your teammates completely in the dark, guessing what the code actually does or what it's supposed to return. Just picture this. Your teammate hands off a massive code base to you.
You're sitting there trying to decipher 10,000 lines of complex logic, but the inputs and outputs are a total mystery because everything is just labeled any. You'd literally have to run the code and watch it break just to figure out what it does. It's a developer's worst nightmare. You'd be totally paralyzed. So what's the elegant fix here? It's a generic variable. In Python, we create this using typevar, and by convention, it's usually just called t. This generic variable safely adapts to whatever data type is passed into it at runtime, and then, here's the crucial part, it locks that type in for the rest of the execution. Our source material uses a really fantastic cultural analogy to explain this. Think of a standard, strict type, like a custom-tailored sherwani. It's made to perfectly fit only one specific person, right? If anyone else tries to put it on, it just doesn't work. But a generic type, that's more like an ihram. It's a universal garment. It instantly adapts to perfectly fit absolutely whoever happens to be wearing it at that exact moment. Another really helpful way to think of generics is just like a simple fill-in-the-blank variable. If you pass a list of strings into your function, that t variable instantly fills in the blank with string. From that millisecond forward, the entire function strictly locks in to treating everything as a string. It gives you the ultimate flexibility of dynamic inputs, paired with the ironclad safety of strict type enforcement. And you can see this brilliantly illustrated in the actual OpenAI source code. If you look closely, they use a generic variable named t-context. Why? Because an AI agent's context could be text, it could be code, it could be almost anything. It's super unpredictable. By using a generic, they enforce strict, safe rules on this wildly unpredictable data without breaking the whole application. Okay, let's tie this all together. Here is your modern Python arsenal. You use @DataClass to instantly spin up clean, boilerplate-free data structures. You use callable to enforce strict behaviors for all your functions. You use typevar to handle unpredictable data with dynamic, super safe generics. And finally, you run a static checker like MyPy over the whole thing. Doing this guarantees that your code is predictable, self-documenting, and practically bulletproof before you even hit run. You've basically just stepped out of the unpredictable, kind of messy world of basic scripting, and you're now fully equipped with the empowering tools of true enterprise-grade architecture. I mean, these are the exact same paradigms used by the top-tier engineers at OpenAI. So the only question left to ask is, now that you actually know the secrets, what are you going to build next? Thanks for hanging out with me for this explainer, and I'll catch you in the next one.